Hello there. You're listening to OYLA, a science podcast for students. We tell stories that make you smarter. Don't forget to subscribe so you don't miss our latest episodes. You can discover even more about science and the world around us in our magazine, so head over to OYLA to check it out.
People try to avoid accidents in their lives. Usually, we strive to control everything and everyone. But in life, chance plays an important role. Hello, friends. Welcome to OYLA Podcast, and today we talk about randomness. The choice of who will play white in chess is more likely to be left to chance than to a judge. The same applies to lotteries and other games that require a fair distribution of winnings. In addition, randomness is extremely important to modern cryptography and, consequently, the work of the internet. First of all, we must clearly understand that randomness is not a characteristic of a single number. We cannot compare the numbers 400 and 397 and say that 397 is more random. Randomness is a characteristic of a numerical sequence. Take two binary sequences, 1 1 1 1 1 1 1 1 0 and 1 0 0 1 1 0 1 0. This sequence is more random than the first one. Why? The closer the sum of all the sequence's numbers is to the mean, the more random the sequence. That is, we must sum up all of the numbers in the sequence and divide the resulting sum by their quantity. In this example, we have 8 digits. In the first case, we get 0.875, in the second, 0.5. The digits 1 and 0 have equal chances to come next. The odds are stacked at 50%. But in the first case, 1 appears more often than 0, and the sum of all the numbers in the sequence divided by their quantity, 0.875, is closer to 1. That is, to the highest value, not to the average. So the second sequence will be more random, where the indicator is 0.5, and where 1 and 0 can equally take advantage of their chances to fall 50-50. This is far from the best way to determine the randomness of a sequence, but from the previous example, we can deduce one of its main characteristics. No number in the sequence should depend on the previous one. It's no good if our random number generator, having given, for example, the number 5, will think, I generated a 5 last time, so now I will opt for some other number. Otherwise, someone is likely to think that this is not a sufficiently random sequence. At any given time, the probability of any possible number appearing must be the same, even the 5 that just came up. Suppose we have 10 numbers. The probability of each number appearing should be 10%. Is a person able to take into account this probability? It turns out that we're not. We'll offer you a simple experiment. Choose a random number from 1 to 10. Did you think of a number? All right, remember it. Now, let's see how good a person is at generating random numbers. We'll tell you up front, humans are very bad at this. Anyone who has played any one-on-one games with the same opponent for long enough knows that sooner or later they become predictable. This applies to chess, checkers, and even fencing. Claude Shannon, an English mathematician and the founder of modern information theory, came up with an algorithm that is now known as Shannon's mind-reading machine. He transformed the assertion of the predictability of the subjective human feelings of players into mathematically proven fact. The gist of the algorithm is as follows. A person writes on a piece of paper either 1 or 0, and the machine makes a prediction of that number. After the machine voices its prediction, the person reveals what was written down, and the machine remembers their chosen number. At first, the machine loses to the person half of the time, as it should. But after about 50 iterations, the machine achieves incredible accuracy in its predictions, 85–95%. Are people really that predictable? Let's go back to the number you chose. Statistically, more than half of you thought of the number 7. If we asked you to think of a number between 1 and 20, about a third of you would think of 17. Between 1 and 100, the most popular random number is 73, and the second most popular is 37. Why does this happen? It seems that, in our heads, we build some kind of complex scheme, according to which we estimate the level of randomness for each number and stop when it seems sufficiently high. It's easy to determine whether 10 is a sufficiently random number. Most would say no. But, in fact, this number is random to exactly the same degree as any other. Moreover, a person cannot generate a random number each time without factoring in the previously chosen number. If you ask the same person to generate another random number, most likely they will not choose 7 again. A random number generator may well pick 7. The coin does not know onto which side it fell last time, and each time, the probability of tails remains 50%. We are unable to come up with random numbers because our brains are always looking for patterns. We try to systematize our knowledge and look for connections. That is why there are championships even in such simple games as rock, paper, scissors. That explains why there are people who are more successful at games than others, although at first glance, it's all decided by chance. Still, any computer program that uses the principle of Shannon's mind-reading machine will defeat a person easily. Random number generators are modules of programs that produce sequences of numbers, pseudo-random and true random. The former are used much more often because such generators are easier to integrate and because they are usually sufficient for most tasks. Random number generators are divided into software-based and hardware-based. Software is just an algorithm, and hardware is an independent hunk of metal that performs only one task, creating random numbers. It seems impossible to implement a program generator of true random numbers, and we will discuss why. It's not just people who try to find patterns. American psychologist Burrhus Frederick Skinner conducted an interesting experiment. He put pigeons into special isolated containers and gave them food at random intervals, independent of the bird's actions. If the bird received food after a given action, such as turning on the spot or beating the corner of the cage with its beak, it would repeat this action in the hope of getting another serving of food. Similar experiments with humans have shown roughly the same result. Imagine a booth with a few buttons and a light bulb. A person is told that his task is to make the bulb light up. In fact, the bulb lights up randomly, and the person has no influence over it. But almost all of the participants in the experiment were convinced that they were able to find a sequence of actions that led to the bulb lighting up. They believed that if they jumped on one foot and clapped their hands or stood on a chair and touched the ceiling, the light would turn on. We can find patterns even where there are none, and that seriously hinders our understanding of randomness. Sometimes it is easier for us to find patterns in a truly random sequence than in one that takes into account this tendency of our minds and adjusts to it. If people want to get a truly random result, they usually use a coin. It meets the disjoint rule. The previous coin toss has no effect on the next. The probability that we will get 4 tails in a row is equal to the probability that we will get tails, heads, heads, tails sequentially. A coin is also exceptional for its extreme honesty. The probability of heads and tails is about the same. A more complex example of randomness is a deck of cards. The number of possible permutations of cards in a deck is 52 factorial, i.e. factorial, for example, 4 factorial equals 4 times 3 times 2 times 1, or about 8 times 10 times. This means that every time you carefully shuffle a deck of cards, you will most likely have a completely unique sequence of cards in your hands, which has not yet been dealt to any person on Earth, and, moreover, will most likely never be dealt again. Pulling a card from a deck, we are able to recognize that there is now 1 card less. We see that, among the remaining 51 cards, there is no, say, Queen of Spades. Each time we take card after card from the deck, we increase the probability that we will be able to guess the next card, but still, this probability is negligible. The measure of this uncertainty, the inability to guess the next element, is called information entropy. The higher the entropy, the more random the sequence. When cards of the same suit appear in the deck one after the other, this indicates an insufficient level of entropy in the deck. Here's our advice if your mom scolds you for your messy room. You can just tell her it's not actually messy, but on a slightly elevated level of entropy. Why do computers need random numbers? First of all, they are often found in games, the location of cards in a deck in solitaire, the sequence of shapes in Tetris, or a randomly generated world in some sandbox game. The pseudo-random number generator is responsible for this. Pseudo because the generator looks for a balance between less random and more random, meaning that its choice is no longer completely random. In games, we risk little and can let the generator do as it wants. But what do we do when it comes to more serious things, like your personal data? Suppose you need a strong password. Here's the problem. The pseudo-random number generator will generate a pseudo-random password for you. This means that a specialist can learn the password generation algorithm and figure it out. In The Art of Intrusion, American hacker Kevin Minnick tells the story of a group of hackers who, in the early 1990s, bought a slot machine of the same series that was then used in Las Vegas. The criminals disassembled it, found the source code, extracted the fragment responsible for the generation of prime numbers, and, on the basis of the decks of cards issued by the slot machine, were able to write a program that forms the same sequences as the program of the machine. Thus, they always knew what cards were planned out by the machine. This is a good example of why pseudo-random number generators are not considered reliable. Only true random number generators are considered to be truly cryptographic. The principle of their work is that they take information from outside the computer. For example, some are based on reading weather data. Others are based on the extraction of arbitrary packets of information from background radiation. The third type is based on the Brownian motion of small particles. The task of true random number generators is to extract randomness from the mine of entropy as quickly as possible. Based on them, you can quickly create secure, unbreakable passwords and keys for large information systems that require a high degree of protection. So, we call randomness something that is beyond our control. But the more one knows of the world, the less one feels that life is full of randomness.
You've been listening to a podcast brought to you by OYLA, a science magazine for students. Please subscribe and check out our website, OYLA, for more information.